All right, so this week, if I recall, we're finishing up the chapter 5 and then doing chapter 6. So that's where we should be in the process. And chapter 5 is designed in a way to sort of walk you through all of the different parts of the system. So logically, the way that I always structure these things is I start at the solar panels and then I work myself sort of left to right, at least in my own mind. So we go from the solar panels to the connectors to the junction box, combiner box, DC disconnect, then the inverters or the charge controller, depending on the system, and then onto the inverter, and then from the inverter to the AC disconnect, then connecting to the service panel, and then the meter. So we're kind of working our way that way. And so the logic, hopefully, is that you see how do each of these things interact with each other. What are the features of each of those products that you might look to see when you're selecting them. Some items you don't have many features at all. A connector is a connector is a connector. Although we do talk about the fact that MC4 is not. It's a class of connectors. It's used like it's a generic term, sort of like Kleenex or Xerox, but they're not. One MC4 is not the same necessarily as another MC4 connector. So you want to make sure that these things have been rated to be intermatable. If they don't, if you don't, then you can have some catastrophic failures. You can have fires because the little connectors inside aren't snugging up against each other, so you might get arcing within that as the electricity is trying to jump across. And that's one of the leading causes of fires within solar arrays is just non-intermatable connectors. And you always have to make a jumper. You're just going to have to do that. So if you think about when you're laying the panels out on a roof, you're going to have your junction box or your combiner box on one end of the string. You're going to have to make a jumper to get the second lead all the way from the other end of the panels down to that. So you're going to be making jumpers in the field and make sure that those connectors are intermatable. Now, I know that we talked about wanting to size the wire in this because I think of all of the different parts, the wire sizing is maybe the most complicated. So I'm going to go ahead and share the whiteboard. And there is a chart as far as wire sizing, how many amps, and that chart is on page 111. So we'll be referencing that chart. Oh, that's right. I've got to move this over into the other screen because it doesn't want me to. My little marker doesn't work or my pen doesn't work on that screen. Okay, so let's say we've got a excuse me, a solar array. So I've got the array up here. And let's say that we're going to have 3 strings. We're going to go into a combiner box. From the combiner box, so this is an old style string inverter system. From the combiner box, I'm going to go to a DC disconnect. And let's assume that DC disconnect is connected to my inverter. And from the inverter, I'm going to go to an AC disconnect. And from the AC disconnect, it's going to hook into my service panel. And then that's going to go out, and then this is my meter. All right, so the question is, this is just an old style, old school string inverter system, grid tied, no batteries. So this is when I first started teaching solar back in, 2012. This is 99% of the systems that we install. They've changed a lot since then, but this is still good for sizing wire. All right, so the first thing we need to know is what size wire do we need here? This is the PV source circuit. The PV source is the wire that goes from the panels to the junction box or to the combiner box. And these are the ones that are just, you're hooking the pigtails together in the solar array and then you're going to pop. So these are usually the only wires that are not in conduit. So these are all of the different connectorized wires. So where do we get our amps? Because the amps are going to be the thing that dictate the size of the wire. Well, we're going to look at the solar panel. And if you look at the solar panel, you're going to see that it has a VOC rating and an ISC rating. And so and then it's going to have a VMP and an IMP. But VOC is the theoretical maximum voltage that panel might generate. So let's just throw a number out there and let's say it's 32 volts DC. And then let's look at the ISC and let's say it's 11.2 amps. So that's the theoretical maximum amperage. Well, you remember when we hook panels together in a string or we hook batteries together in a string, voltage increases, but amps remain the same, right? When you make a series connection, which is what a string is, voltage increases and amps remain the same. Well, then that means that the amps for one panel is the amps for the string. Doesn't matter how many panels you've hooked together, right? Amps for one panel is going to be the amps for the string. So the theoretical maximum amperage for each of these strings coming into the combiner box is going to be 11.2 amps. But the National Electrical Code always requires that you put a safety margin. So it's going to require 1.25. So we multiply that, and that's the National Electrical Code safety margin. So let me grab my little calculator over here. And if it's 11.2 amps times 1.25, and remember, it's not going to be generating 11.2. That's the VM, that's the ISC. It's probably going to be operating at the IMP. And the IMP here might be, let's say, 10.7 amps. It's going to be less. But we want to take the maximum, right? We're going to take the worst case scenario. So we'll always use the ISC because that's the theoretical maximum. So now 11.2 times 1.25, we get 14 amps. But we're not done because the National Electrical Code also says for solar, and this is particular to solar, because the sunlight is variable, we want a second safety margin of 1.25. So that's the solar variability. And the reason about that, the logic there, is all of these numbers are based on 1,000 watts per square meter. But we know that at the outside edge of the Earth's atmosphere, the sunlight has about 1,300 watts per square meter. And I've gone out on a clear winter's day and gotten readings of like 1,200 watts per square meter. So the assumption is, okay, on a normal day, we're going to lose about 300 watts as it goes through the atmosphere to reflection, to scattering, to all of that. But it could be higher. Could be higher. It could be 1,200. Could be 12. So we're going to put another multiplier, 1.25, saying that it might be as high as 1,250. Be very rare, but just to be safe. So we're taking the 14 amps times 1.25, and it's now 17.5 amps. So what usually begs the question is, when do we apply that solar variable? And it's as long we apply it until you hit the first piece of electronics. The first piece of electronics that controls the output of that solar panel. So that might be the charge controller in a standalone system, because as soon as it gets into the charge controller, now it's going to control its output. But it might be a microinverter. If it's a microinverter, then that's connected directly to the panel. So we never use that second 1.25 because the microinverter is already controlling. Power optimizer, already controlling. So that's something that we we would deal with. So we're just going to, it's as soon as you hit that first electronic device, you stop doing that second 1.25. This is something everybody forgets. You know, you need to multiply time twice. So what we've now said is this poor little thing is now going to be generating 17.5 amps. So I need wire that can handle 17.5 amps. So if I look up in the table on 111, and you always read from the first column. And the reason for that is because let's say I've got a device here. I've got a combiner box and a DC disconnect, right? So this is my DC disconnect. This is my combiner. And I've got wire connecting those two. Well, the ampacity rating for that section is not just the wire, but it's the connection point inside that combiner box and the connection point inside that DC disconnect. And you'll see in the chart on page 111, the wire can be rated for 3 different temperatures: 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius. And if we get a higher temperature rated wire like THHN or used to or PV wire, it can carry more amps than the less highly temperature rated wire. So let's say that I needed 17.5 amps. I might go and say, well, okay, I could use 14 gauge because it's rated for 25 amps if I'm using the high temperature wire. But I don't know what those connection points are rated for. They could be only rated for 60. So that becomes the weak link in that connection. So let's always assume the worst case scenario. Let's always assume that our wire and our connection points are only rated for 60 degrees Celsius. That way you never go wrong. So if I'm reading from the first chart or first column and I need 17.5 amps, the smallest wire I can use is 12 gauge, right? Because 12 gauge wire, when I'm reading from the 60 degree column, is rated for 20 amps. So I would use 12 gauge wire. Well, it turns out that the panels themselves generally in today's market come with 12 gauge wire. So that wire is going to be able to handle the amp output even with the correction factors. So that's just kind of built into the pie. So that's going to be 12 gauge wire. This wire here, number 12, AWG. So that's, and we made our jumpers that way, and now we're going to terminate them in the combiner box. Now, let's say that the combiner box has a fuse in it or a breaker. What size breaker do we need if we're connecting into that breaker? Well, once again, 17.5 amps, we round up to the next commercially available size breaker. So we would have 20 amp fuses or 20 amp breakers in here, right? And now what we need to check is to make sure that the breakers or the fuses do not exceed the capacity of the wire that's feeding them. So we've got 20 amp wire feeding 20 amp breakers, so we're fine. Okay, so we've got 12 gauge here, 20 amp breakers or 20 amp fuses in the combiner box. So now what happens in the combiner box? Well, as its name says, the circuits are now combined. So they're combined in parallel. We have 3 circuits coming in, 3 strings coming in. We only have 1 pair of wires leaving. So they're hooked up in parallel. When we hook up in parallel, amps increase, but voltage remains the same. We know that it's 17.5 coming in. We know that there are 3 of them. So it's going to be 17.5 times 3, or 52.5 amps. So the wire leaving needs to be rated for 52.5 amps. So what size wire do we select? If we look at the table, it's going to be 6 gauge wire, right? It's rated for 55 amps. Could be 6 gauge. We could use 4 gauge, right? That's not a problem. You can always go with bigger wire. Doesn't cause any problem, except it might be harder to pull and harder to terminate. But we go with 6 gauge wire. Now, what happens when we come in to the DC disconnect? Well, we if there's a fuse or a breaker here, what size fuse or breaker? We round up to the next commercially available size. I think there's a 55 amp fuse. So we put a 55 amp fuse there. Once again, we've got 55 amp wire, 55 amp overcurrent protection. We're fine. What about the rating of the box itself? Usually these DC disconnects come rated 30 amp, 60 amp, 100 amp, 200 amp. So we wouldn't want to use a 30 amp box. So we'd probably use the 60 amp. And if it's already connected to the inverter, it's going to be sized based on the capacity of the inverter. So that's just the metal itself within the box. How much amperage can it handle before it melts or it does something bad? So in this case, I've got a 60 amp box, a 55 amp fuse being fed by number 6 gauge wire. Okay, so I've sized the wire there. Now, here's my inverter. What happens in the inverter? Does something change as it's leaving? And the answer is yeah. Now it's being converted to AC from DC, but it's also being converted to whatever the voltage is. And in this case, if it's a house like single phase, we're going to say it's 240 volts AC. So the output is going to be 240 volts. Now, let's say that this is a 10 kW inverter, 10,000 watts. Watts equals amps times volts. So amps would be watts divided by volts. So if I've got 10,000 watts divided by 240 volts, then the output divided by 240 gives me 41.67. Right now, I could have shortcutted that by just simply looking at my inverter specs and it'll tell me what's the output in amps. So I could do that. But this is a quick way. 41.67 amps is the maximum output of that. All right. So, but the NEC always requires 1.25. 1.25. Do we need a second 1.25? No, because solar variability is not a factor. The inverter is determining how much is being output. So 41.67 times 1.25 gives me 52.09 amps. All right, so it just sort of turns out that our amperage is pretty similar. It could have been wildly different. 52, well, we're going to stick with 6 gauge wire, right? Because that's rated to 55. You clear on that? So,
Yes, I'm clear.
okay. And I think we're joined. I don't have the participants up. Yep. Cheryl is on here too. Cheryl, are you following us okay? Do you have the ability to speak?
Hi, can you hear me?
Yep. Yep. That's good. Okay. So is this making
I'm
sense?
Yes, it is, and I am not being very participative because I'm working at the same time. So thank you.
Okay. You must be younger than me. You're able to multitask. So,
I'm trying.
okay. All right. So we've got number 6 wire coming in. Now, if we have a fuse, what fuse again? Well, it was 52 point. I think I covered it over here. Yeah, 52.09. So it's going to be 55. So it's going to be a 55 amp fuse, 60 amp box. Now we come in here. Does anything change in the ampacity of that wire? No, it's just a switch. So we're going to follow up with 6-gauge wire. And then what size breaker would we need here in the circuit breaker box? Well, we've already determined you round up to the next available and we'd have a 55 amp circuit breaker. That might cause us a problem in this service panel. And the reason for that is what's referred to as the 120% rule. Okay, 120% rule basically means that this box, this circuit breaker panel box, has an ampacity rating. That ampacity rating, let's say that it's 200 amps. It's been rated for 200 amps. And we have 200 amp service coming in from the utility. Well, you would look at that and you might realize, or you might think that you've already met all of the capacity of that particular box because we've got 200 amp service and a 200 amp rating. But the NEC allows us to go to 120%. 120% of 200, that would be 240. So we could actually come in with up to 40 amps of power into this second breaker and not violate the National Electrical Code. Problem is, we're needing 55 amps. So we'd have to do several things here. We would have to either upgrade the box itself, swap out the box, maybe go to a 225 amp box, which would mean that I could go 25 plus 40, which would give me 65 amps. That would work. If it's already rated for 225, great. No problem. We're fine at the 55 amps. Another option would be to replace the main breaker. Instead of 200 amp service, maybe go 150 amps. But as long as between the two, we don't overdo 120% of the rating of the box, that's all we're worried about. So that's the 120% rule. And that's one reason why we always put the breaker as far away from the main as possible, because then you're feeding it and it's going out to your loads. It's coming in this way. It's going out to the loads, but the ampacity is not doubling up on the same wire or the same part of the bus bar. So that's what we're doing is we always come in at the bottom with our service panel, with our array. And of course, the main is up typically at the top. So this is how you would size the wire. Any questions on that? I'll do another quick little one here. If I wanted to size wire, let's say I've got a solar array here. And what's more typical is, let's say I have three strings, but now I want to come in with 3 strings and continue those down to my inverter. So I'm going into my DC disconnect, going to my inverter. From the inverter, I go to my AC disconnect. From the AC disconnect, I'm going to go into the service panel here and then out to the meter. So this might be a Solar Edge or something like that. All right, but I've got 3 strings. So let's say that I've looked at it and my ISC is 10.3 amps. We would take 10.3 times 1.25 times 1.25, and we would get times 1.25. And I'm getting 16.09. So the wire here would still, if we look at the diagram on page 111, 12 gauge wire is still fine. So this would be number 12. But now we're not making a parallel connection. So the ampacity just simply passes right through. So this would be 16.09 amps. You could go with 12 gauge wire and you'd be fine. But one of my recommendations to you is never use smaller than 10 gauge wire when you're designing your system. And the reason for that is the difference in cost between 12 gauge wire and 10 gauge wire is minuscule, and it's going to save you a lot of problems. So just put in your head, call it Jay's rule or whatever. Just don't use anything less than 10 gauge. Now we already violated that with the jumpers, but that's just because the panels came with 12 gauge wire. So, all right. So here we could go with 12 gauge, but let's just say we're going to go with 10 gauge wire. All right. Okay. So that is, and one of the reasons is, what if this wire was exposed to sunlight and it's in conduit lying on the deck of the roof? Well, on page 112, there are some temperature correction factors. So what you do, if it's lying on the roof, you have to add 33 degrees Celsius. I think that's right. I'm going by memory here. Pretty sure I'm looking through this. So is greater than, I'm just double checking. I'm reading through. Oh, wires and conduit. Yeah, 33 degrees. So let's say that this is in a conduit and these wires are sitting here. Well, there's a couple of issues because they'll all be in the same conduit and they're lying on the deck and they're exposed to sunlight. So you look up and you find out that the hottest temperature ever experienced in this particular location is 38 degrees Celsius. But because they're lying on the roof, we've got to add 33 degrees Celsius. So now we've got a temperature of 71 degrees Celsius. Well, if you look at the temperature correction table here on page 112, and we read from the first column, well, we can't read from the first column. We've got to go over here. So it's 0.5. So 0.5. So that basically means that the wire is only capable of handling half the amps. So in this case, I would say 16.09. And if I divide it by 0.5, I'm going to get 32.18 amps. So now I need wire capable of carrying 32.18 amps. So if I look at the table on page 111, what wire? Well, it's probably going to be 8 gauge wire because 40 is reading from column 1. But we're not done yet because we've got essentially 6 wires that are in this conduit. And so there's another table here on page 114 that says if you've got 4 to 6 wires, you've got to derate this by 80%. So 32.18 divided by 0.8 gives me 40.225. So technically, we would have to get wire that's rated above 40. So we couldn't use 8 gauge. We'd have to go to 6 gauge wire. So this would have to go to 6 gauge wire, which is expensive. So this is a good reason why you don't want to run your conduit on the deck of the roof and exposed to sunlight. Now in the field, they actually have these offsets where you can keep it like 1 inch off the deck of the roof. There's a picture of it on page 111 or 113. And so you can just run your conduit slightly elevated off the roof and you would avoid that problem. In that case, we wouldn't have the temperature issue, but we would still have the conduit fill issue. So if we started at 16.09 and had to divide by 0.8 because there are 6 wires in there, 16.09 divided by 0.8 is 20 20.1125. Well, we're still fine if we use 10 gauge wire. If we use 12 gauge wire, we're a little bit iffy. So that's another good reason for using 10 gauge wire. Okay, I'm sure I've thoroughly confused you on all of that, but this is just what you do. So in this case, let's assume it's not exposed to sunlight. We're going to use 10 gauge wire there. We come into our DC disconnect. If we have fuses or breakers in there, what size fuse or break? Well, it's 16.09 amps. We round up to the next available size. So we'd have 20 amp breakers or 20 amp fuses in here because that's the next available size. And then we go into the inverter. Well, let's say that this is a smaller system. So let's just say it has say a 5 kW inverter. What's the output of the 5 kW? 5,000 watts divided by 240 volts equals 20.83 amps times 1.25 because we got to start over again. And I get 26. So 26 amps coming out of here. What size wire? Well, 10 gauge would work, right? AWG, 10 gauge. Then we go to our AC disconnect. What size fuse or breaker would we have in here? 26 amps. We round up to the next available. That's going to be 30 amp. After the AC disconnect, does anything change? Nope. So it's still going to be 26 amps. So it's still going to be 10 gauge. What size breaker do we have in our service panel? Well, it's going to be 30 amps because we round up to the next available. Is 30 amps okay if it's a 200 amp service panel with 200 amp service from the utility? Yeah, because of the 120% rule, we can go up to 40 amps. So we're fine. Okay, so you've just designed your whole system. Or I did it and you watched. So is that so I know I went through it quickly and it can there's like I said at the outset, I don't think there's anything really hard about this. It's just a lot of things to remember. A lot of little bits. Like when you're sizing the wire, the first thing you got to remember is the 1.25 safety margin. And then before you get to your first electronic device, you've got a second 1.25 solar variability margin. So that's one thing that you got to plug in. Then you've got to worry about temperature corrections, conduit fill corrections, things like that. And the rest of it is mostly just looking things up in tables. So, and then of course the 120% rule, which everybody runs afoul of when you get to the service panel. So any questions about that there?
I have one on your drawing.
Oop, I lost your visual or your sound. You're muted there.
Okay, I'm sorry. There on the bottom left, there's three wires coming out, uh, but you said there were six wires.
Yeah. Yeah. In a
But
one line drawing, you typically just, there's going to be a positive and a negative,
right, okay, but
but
both
you
ways.
just, yeah, you just indicate with one. It's, there's usually what they call a one line drawing is if I've got a circuit and it doesn't really matter if it's DC, if I do a wire like that, it's probably going to be a positive wire and a negative wire. But over here in AC, there's probably going to be three wires, right? Because there's line one, line two, and neutral. So that one line indicates three wires.
Okay, gotcha. Gotcha.
But yeah, and so the ground is also typically in there, but that's a non-current carrying wire, so we can ignore that as far as capacity, because it's never supposed to carry any power unless there's a problem. So, yeah. Now there's also another drawing that they'll usually refer to as a 3-line drawing, and those are going to be more detailed. So you might have a picture here of your DC disconnect, and you might have the positive wire coming in here and connecting, and the negative wire coming in here and connecting. And it's going to show you, and then an equipment ground wire coming into this bus bar. So the 3-line drawing is going to show you all the connection points and much more detail. So the 1-line drawing is just gives you a sense of the architecture of the system, but it's not showing you all the wires. When you submit plans to the authority having jurisdiction, which would be your code enforcement office or whoever's giving you your permits, they're going to always want to see a 1-line drawing. They're going to want to see something that tells them, okay, what's this thing look like? And they'll already know that you're not showing them all the wires. Okay, so that's kind of wiring. If we go through some of the other issues here, the sine waves, I think we're okay there. I want to move through it pretty quickly because I want to get to the chapter 6. I don't think there's anything other that's kind of difficult in chapter 5. Then we get into conducting a site survey, chapter 6. I think chapter 6 is pretty intuitive. It's basically, okay, what questions do you need to answer if you're going out to a site and you want to install solar? All right, where are you going to put it? How's it going to be oriented? Is there going to be shading? Where are we going to put all of the bits? Is it going to be a roof mounted system? Is it going to be a ground mounted system? Is there going to be tracking on the system? Well, in the Northern Hemisphere, it's almost always best to orient your panels solar south, right? The sun always tracks in the southern part of the sky. In the summer, it's going to be more overhead, but it's still going to be to the south. In the winter, it's going to be lower on the horizon, but it's still going to be to the south. Now, if you're doing this in Australia, it's the opposite. You're going to face everything north. The further you get away from the equator, the more of an angle you're going to want for your panels. At the North Pole, you can go vertical, just straight up and down. At the equator, it'll be flat because the sun's mostly going to be tracking just overhead. At the North Pole, it's going to be on the horizon, and so you want as close to vertical. I know when I was up in Alaska, I saw a lot of solar panels on the side of buildings. They just put them on the side. Yeah, it makes sense. Of course, at the equator, everything's just lying flat. So you can get a little more efficiency that way for sure. You can put the panels closer together. If you've got multiple rows, you can sort of see, like, let's assume my hands here are rows of panels. Well, the further north you go, the longer shadow that first one's going to cast. So you need to move these things further and further apart. At the equator, they're lying flat. They could be right next to each other. So you get less, you need more space the further north you go. The other issue is what is south, right? There's a difference between magnetic south and solar south. And when you're at the Mississippi River, it just sort of happens those two align, where the magnetic is essentially the electromagnetic point that we consider the North Pole. But that electromagnetic field that surrounds the Earth moves around. It shifts over time. Right now it's moving, I guess, towards Alaska. And so north is not north. Magnetic north is different than solar north. And solar south is different than magnetic south. So you have to make those adjustments. In our lifetime, it's shifted. The magnetic fields have shifted more than 1 degree. So, and eventually they're going to flop, they're going to change, where the North Pole will actually be the South Pole and the South Pole will actually be the North Pole. And this has happened many times before. What what impact does that have on the world? I'm sure it's coming to an end, but not because of that. It's really just your compass is going to point the other direction. It doesn't really matter. But navigation gets a little bit screwed up. But now we have GPS, so a lot of people are using solar, as opposed to magnetic. But in the old days, pilots had to make these adjustments all the time. And that's why we had these declination maps, is the pilots would always be adjusting magnetic versus solar. Otherwise, they'd follow their compass and they'd be heading to Iceland and they'd end up in England, So you just want to make sure. Okay, so what's the ideal orientation or angle of the panel? Well, if you think about it, at the equator, we said it's flat. At the North Pole, it's vertical. So it's going to be whatever the latitude is. So it'd be 90 degrees at the North Pole. It'd be 0 degrees at the equator. And here, where I am in Columbus, Ohio, we're at right about 40 degrees north latitude. So the ideal average orientation would be 40 degrees. Because at the equinoxes, spring and the autumnal, the sun would be exactly at a 90-degree angle to the solar panel if the panel were angled at 40 degrees. But that assumes that the days are all the same and that the amount of sunlight is all the same. Well, we know that in the summertime, the days are longer, right? The days get shorter in the winter and longer in the summer. And also there tends to be more sunlight in the summer months as opposed to the winter months. So we typically would have what we call a summer bias. You take latitude minus 15 degrees so that you're laying it a little more flat because you're going to generate more power over the course of the year by giving it a summer bias. That's if you're a grid-tied system. That's if you can continue to build up. Because the way that my grid-tied system here in the house works, I usually, for 9 months out of the year, I either have zero bill or I can build up a credit. And that credit carries forward month after month until it gets used up. In the winter months, we tend to go less. We're not generating as much power. And we use, electric heat and stuff like that. So we use up that credit in the winter. But if you had a utility that doesn't carry over your credit from one month to the next, you might want to size your system to make sure you use every month what you generate every month. So maximizing your solar may not be the biggest issue. You want power when you need the power. Same thing with a standalone system. Standalone system, you don't build up any credits and you don't sell anything back to the utility. So you want the power to be generated when you need the power. So for instance, at our farm, we used to use more power in the winter than we did in the summer because we didn't have air conditioning, but we had a lot of livestock, and the livestock had heated buckets and things like that. We used electric warmers in there for them. So our power bill was a lot more in the wintertime than it was in the summertime. So we might want to have a winter bias to generate more power in the winter, less power in the summer, less power overall, but we're going to generate the power when we need the power. And that's something that you'll get with a standalone system a lot. And that's why you might have a winter bias. But most of the time with grid-tied systems, you're going to have a summer bias because you want to maximize. So what's the angle? Well, ideally here in Columbus, Ohio, it'd be 40 degrees minus 15, so a 25-degree angle, ideally facing south. Now, if you're going to set your solar array on the top of your roof, guess what your angle is and guess what your orientation is going to be. It's going to be whatever angle your house is facing, and it's going to be whatever it's going to be whatever the angle of the roof is. You're not going to be able to change that. So you're just going to live with what you got. But a ground-mounted system, you can play with it. You can make things work. So that's an advantage of ground-mounted systems, is you can maximize. Rooftop systems, you get what you get. So. Let me see. I'm sort of flipping through here. We talked about inner row shading. It's usually about a 1-to-3 ratio. So if it's 6 feet high, you want to move it back 18 feet. That's in the mid latitudes, 40 degrees. If you got further north, it'd be further, maybe 1-to-4. Get further south, it'd be less, 1-to-2. So that's kind of all the thought we put into that. Solar Pathfinder is a tool where we'll actually do that in a lab where you'll measure your shading. It's a nice tool. And I don't want to get too much into there's a whole section here about total solar resource fraction. The whole concept of total solar resource is if everything was perfect, if the orientation was perfect and there was no shading, this is the amount of power that site has available. Then you simply deduct out shading issues and the difference in orientation between perfect and what you're dealing with. And that's your total solar resource. And the reason it's important is sometimes you'll get grants or things like that that'll say, you've got to have a total solar resource fraction of at least 80%. Otherwise, we're not going to award this grant to you because we don't want to give you money for crappy locations. We've only got so much money. We want it to be used well. So that's where that usually comes into play. And then we get into NEMA ratings for enclosures. The NEMA ratings for enclosures, we're usually dealing with 3 or 3R. That's just an outside. But you'll see there's a chart on page 173 where it talks about all the different types of ratings. So you'll oftentimes hear it's NEMA 3 rated, for outdoor installations. And then the service panel, we talked about the 120% rule. And if you don't understand that, just review some of that. There's some questions in the book about that. The difference between a load side connection and a line side connection. Let me open up my whiteboard here. And it's pretty straightforward. There it is. Yeah. So what is a load side? What is a line side? Well, if this is my service panel, and here's my main breaker, and it's going out to the meter, and here's my inverter, and I know there's an AC disconnect in between there, but I don't want to confuse things. I would go from my inverter if I'm going on the customer side of the main breaker. It's considered a load side connection. It's on the load side of the main breaker. If I have to connect in somewhere between the main breaker and the meter, then this is considered a line side or a supply side connection. And that's on the supply or the line side of the main breaker. Now, the load side is always going to be cheaper. It's always going to be cheaper because I can just turn off my main and I can hook in a breaker and I can install this myself. It's no big deal. In fact, we'll do that in our labs when you're here in Marietta. It's piece of cake. Just turn off the main breaker, attach your wires to another circuit breaker, and snap that puppy in there, and you're fine. Easy peasy. But if I have to make a line side connection, I've got to contact the utility. I've got to have my service turned off. You're going to have to get an electrician because now it's a real thing. And they're going to have to cut in there and put some sort of tap into these wires and make a connection out here. And so it becomes much more expensive. Either one works, but the further you get away from the lines, the load side, the more expensive it gets. So why would I do a line side versus a load side? Usually it's because my system is too big to fit here into my service panel. So if I've got a 200 amp service panel and I've got a 200 amp breaker here, and I want to come in with the 55 amps like we talked about in our example, I can't do it. I can only go to 40. So I would have to come up here. I'd have to do a line side connection. So none of this could happen. I'd have to make my connection here, and this would be 55 amps. And that's fine. We're not affecting the bus bar, which is the thing here that's rated 200 amps, because the power is going to flow here. If I don't need it for my load, it's going to go out there onto the grid. If I need it for my load, it's going to flow out here to the loads. So this is a line side or supply side connection, and this is a load side. And if possible, we want to go with load side. Now, one other alternative, which is happening now more and more, is the National Electrical Code now requires at the meter that there be a utility emergency disconnect. Now, there's going to be a bus bar here, and there's usually going to be your wire that goes from the bottom of the bus bar, and it goes in, and it connects into your service panel, and it connects to your main, right? So you've now basically put another panel, because these things usually have like space for four, might be more, but you might have 4 double pole breakers locations in this box. This is now your new main. But all of a sudden, because these are newly required, if you're putting in a solar array, you might have to install one of these. So that's going to require an electrician. But it's not as expensive as replacing your service panel. So you're just going to get a new meter box. You're going to have to turn off your service. They're going to install this thing. And then there's going to be 4 empty breakers right here. Well, that's an awfully nice place to hook. This is my AC disconnect. This is my inverter. Well, then I can hook right in here. And I don't have to mess. I don't have to be drilling holes in the wall to get to my service panel. I can just hook into the empty port out here at the meter. That's really nice. You can keep everything outside. The problem is if we've kept everything outside, my $2,000 inverter might be sitting here attached to my outside wall, and somebody with, some wire cutters could walk away with a $2,000 inverter if they so choose. So you might want to put a locked cabinet or something like that. That would work, but it's going to add more cost to it. For a microinverter system, this is a really super idea, because your microinverters are going to be attached up here on your array on the roof, and then you're just going to come down to your AC disconnect and hook straight in there. So there's nothing really for anyone to steal in that system. So it's a really lovely place to make your connection. Okay. All right. So I think we have confused everybody for a long enough period of time, and got through chapters 5 and 6. Any questions before we call it a day here?
When does it become economical to use the tracking devices on the solar panels on a land-based around our area? Is that a good thing, or is that just for other, like I can see where in Alaska or places where there's a big angle, it could really potentially help, I guess.
I would say the minute you have a full-time maintenance person on staff, that's when it becomes economical to have a tracking system.
Okay.
Almost never in a residential environment does it make any sense. They'll tell you that it adds 15% to the cost of your system to put in tracking, and it'll produce 20% more power or whatever. If you need 20% more power, just put in a few more solar panels. It's the maintenance issue that's the biggest thing, because these things require servicing. They do break down. So utilities, they'll put in tracking systems because they've got full-time staff. And so it makes sense for them to do it because they're constantly monitoring and maintaining these things anyway. But for a homeowner, nah, I've never seen a tracking system that makes logical sense. So the big advantage is there's no maintenance, of solar. So, so now you've just given yourself a headache. And most of them that I've seen installed in commercial settings, the tracking system is stopped at the place where it broke down and no one's ever changed it. So as soon as that tracking system breaks, that's just its new permanent location because nobody's ever gone out. And sometimes you'll get some of these really nice on poles that are tracking and they're dual axis tracking and they look really pretty, but they're always just stopped in whatever place that they broke. So I just saved you lots of money. Don't do that.
All right. Where's that impressive solar array over there right across from Ravenswood in Ohio? It's huge and it has tracking on it. I was watching as I go by, it shifts all the time. I thought that's pretty cool. So
yeah, those are normally going to be east-west facing. So the arm, it's like if all the panels are on this big arm and in the morning they're all facing east. And then at noon, it'll have laid down flat. And then, my arm doesn't bend that way, but in the evening, it'll be facing west. And there are a couple of advantages of those for large arrays. One is that they dump the snow off, over the course of the day if you've got snow. But they also do even out the generation of power. And for utilities, that could be a bigger issue. They want power more consistently throughout the day, as opposed to they're not selling it back to anybody. They just need the power when they need it. And now there are some mechanical tracking, not necessarily on the day, but if you wanted to do seasonal for a ground mounted system, for a small ground mounted, where you can just take the whole array and get a couple of people and lower it down in the summer and put the pins back in, and rebolt it. So you just have 3 holes with the bolts and so you can mechanically change it 2 or 3 times a year. Well, there's no maintenance there, but you've got to shift these things. If you've got 10 panels, maybe even 15 panels, that's not a big deal. But if you've got 100, you're not going to do that. So, all right. Okay. So I'll see you guys next Tuesday. And hopefully, as per always, if you have any questions, just drop me an email throughout the week.
Okay, Jay, thanks so much.
Sure thing. Take care.